Hello students, let's start today with the relationship between equilibrium constant, reaction quotient and Gibbs energy. We know that the value of Kc for a reaction does not depend on the rate of the reaction. Also, we have read in thermodynamics chapter, considering change in Gibbs energy delta G, if the value is negative, the reaction is spontaneous in nature. The reaction is spontaneous in nature means the reaction proceeds in the forward direction. The value of delta G is positive, then the reaction is non-spontaneous in nature. That means the reaction, if it proceeds in the backward direction there. And when the value of delta G is equal to 0, the reaction has attained equilibrium condition there. So we can find the mathematical expression of this thermodynamic view of equilibrium by the following equation. Delta G equals to delta G in its standard state plus RT natural log Q, where delta G in its standard state is standard Gibbs energy. At equilibrium, when the value of delta G equals to 0 and Q equals to Kc, in that case, equation 7.21 becomes delta G equals to delta G in its standard state plus RT natural log of K. Here the value of delta G equals to 0. Therefore, delta G in its standard state equals to minus RT natural log of K. If I need to convert natural log to the base 10, I need to multiply it by a factor 2.303. So the value of delta G equals to minus 2.303 RT log K. So we'll apply this formula in the numerical problem. So look at the problem 7.10. The question is, the value of delta G for the phosphorylation of glucose in glycolysis is 13.8 kilojoules per mole. Find the value of Kc at 298 Kelvin. So here delta G is given in kilojoules per mole. We need to convert that to joules per mole. I multiply it by 10 raised to 3. So the delta G value comes out to be 13.8 into 10 raised to 3 joules per mole. We know the formula delta G equals to minus 2.303 RT log K. We'll take the value of R here as 8.314 joules per mole per Kelvin. Temperature is 298 Kelvin, and we'll find out the value of log K. So, and then after we'll calculate K, which will be equal to anti-log of the value which you get. And the final answer Kc here is equal to 3.81 into 10 raised to minus 3. Look at the next problem. Hydrolysis of sucrose gives sucrose plus water gives glucose plus fructose. Kc for the reaction is 2 into 10 raised to 13 at 300 Kelvin. Calculate delta G at 300 Kelvin. So we'll put in the formula delta G equals to minus 2.303 RT log K, and I get, on substituting, the values of delta G here as minus 7.64 into 10 raised to 4 joules per mole. Hope it's clear. Let's come to the next part, that is the factors affecting equilibrium. So a change in equilibrium is affected by the following factors. First factor is change of concentration of either any reactant or product. Second is change of temperature of the system. Third is change of pressure on the system. Fourth, addition of catalyst. And the last one is addition of some inert gas. The effect of change of concentration, pressure, and temperature on equilibrium is predicted with the help of a principle known as Lee-Chatelier's principle. First, we'll discuss about the effect of adding catalyst on the equilibrium. The addition of catalyst does not disturb the equilibrium. However, it helps in the attainment of equilibrium quickly. Let's have a quick look of effect of adding an inert gas to a reaction mixture in equilibrium. If I consider the dissociation equilibrium PCl5 getting dissociated to PCl3 plus Cl2, on applying the law of chemical equilibrium, Kc is equal to molar concentration of PCl3 into molar concentration of Cl2 upon molar concentration of PCl5. If the reaction takes place at constant volume, that is in a closed vessel, addition of an inert gas like nitrogen, helium, argon will not change the molar concentrations of the reactants and products. Hence, the state of equilibrium remains unaffected. If the reaction takes place at constant pressure, addition of inert gas must accompany an increase in the total volume to keep pressure constant. So at equilibrium, the molar concentration of each of the reactants and products will decrease since there are two concentration terms in the numerator and only one in the denominator. Therefore, Kc should decrease, but Kc is constant at constant temperature. Hence, to keep Kc constant, either PCl5 should decrease or PCl3 and Cl2 should increase. And this can happen only if more of PCl5 gets dissociated to give PCl3 and Cl2. Hence, the dissociation increases with the addition of an inert gas. To sum up, addition of inert gas at constant volume has no effect on the state of equilibrium. Whereas at constant pressure, the equilibrium shifts towards larger number of moles. Let's have a quick look at the Lee-Chatelier's principle. And it was first proposed by a French chemist, Lee Chatelier, in 1884. And after his name, this generalization is known as Lee Chatelier's principle. And it states that if a system in equilibrium is subjected to a change of concentration, temperature, or pressure, the equilibrium shifts in a direction that tends to undo the effect of the change imposed in accordance with Lee Chatelier's principle. So let us consider the factors. The first factor which we'll consider is effect of change of concentration. So if you consider a general reaction, A plus B gives C plus D. Addition of reactants, more reactants, it will tend the reaction to proceed in the forward direction. And addition of more products, it will tend the reaction to proceed in the backward direction there. I take an example of hydrogen reacting with iodine. H2 plus I2 gives 2Hi. A very simple example. If I add more of hydrogen or if I add more of iodine, the reaction goes in the forward direction there. But if I add more of Hi, the reaction proceeds in the backward direction. So to sum up, if in a reaction in equilibrium, the concentration of any reactant is increased, the equilibrium shifts in the forward direction. On the other hand, if the concentration of any product is increased, the equilibrium shifts in the backward direction there. The reverse happens if the concentrations are decreased. Let's come to the second factor, and the second factor is effect of change of temperature. The change of temperature usually alters the state of equilibrium for only those reactions in which either heat is evolved, that is, the reaction is exothermic in nature, or heat is absorbed, the reaction is endothermic in nature. Now, if the forward reaction, in fact, for every such reaction, there are two opposing reactions. If the forward reaction is exothermic, the backward reaction will be endothermic and vice versa. So you can consider an exothermic reaction. N2 plus 3H2 gives 2NH3. the value of delta H here is minus 92.4 kilojoules per mole. So here the reaction is exothermic in nature. So for exothermic reactions, remember in mind, low temperature is favorable. So if you are applying low temperature, the reaction favors the forward direction there. But if you apply here a high temperature, instead of proceeding in the forward direction, the reaction proceeds in the backward direction there. So the effect of increase in temperature in case of exothermic reaction, the reaction is favored in the backward direction. Low temperature is favorable. Whereas for endothermic reactions, high temperature is favorable and the reaction proceeds in the forward direction there for endothermic reactions. Look at this effect of temperature on equilibrium for the reaction. NO2 is in equilibrium with that of N2O4. So you can make this NO2, form this NO2 gas on treatment of copper turnings with that of concentrated nitric acid. So you can take two test tubes and you can collect the fumes of nitrogen dioxide in two different test tubes and take three beakers. In one beaker you put freezing mixture, in second beaker keep water at room temperature, and third beaker keep water at the boiling temperature there. Now, after you collect the fumes of nitrogen dioxide in both the test tubes, you put both the test tubes in beaker number 2, that is at in water that is present at room temperature 298 Kelvin for 8 to 10 minutes. Then you take one test tube and put it in beaker number 1 and another test tube you put it in beaker number 2. Beaker number 1 is having freezing mixture and beaker number 2 is having boiling water there. So when I put the NO2 in that of beaker number 1, so there it is the freezing mixture that is available there. So in that case, the formation of N2O4 will be there because the reaction is here exothermic in nature. So when I am putting at low temperature, the reaction favors the formation of N2O4 and the fumes, that is dark brown fumes, the intensity of it becomes less. But when I put it in water at 363 Kelvin, that is in beaker number 3, nitrogen dioxide, when I put it in boiling water there, in that case, the intensity of nitrogen dioxide, it becomes more because the reaction proceeds in the backward direction, as this is an example of exothermic reaction. So if I'm providing high temperature, the reaction proceeds in the backward direction and you can see the intensity of the brown fumes increases in this beaker number 3. So this is the example to illustrate the effect of temperature on equilibrium for the reaction. Next, let us come to the next factor, that is effect of pressure change. So for the effect of pressure change, you consider this reaction. Carbon monoxide reacts with 3 moles of H2 to form CH4 plus H2O. All are present in gaseous state. Now see the number of moles on the product side. There are 2 moles on the product side and 4 moles on the reactant side. Compare the number of moles on the product with that of the reactant side. If the number of moles on the product is less in comparison to that of the product side, with increase in pressure, the reaction proceeds in the forward direction. As in this case, number of moles on the product side is 2 and number of moles on the reactant side is 4. So 2 is less than 4. So with increase in pressure, the reaction proceeds in the forward direction there. So this is the effect of pressure change. I give another example. Look at this. Carbon reacts with carbon dioxide to form 2 moles of CO. Compare the number of moles, gaseous always, solid is not considered. So number of moles on product side is 2 and number of moles on reactant side is 1. So number of moles on product side is greater in comparison to the number of moles on the reactant side. So with increase in pressure, the reaction proceeds in the backward direction. It goes in the reverse direction because the number of moles of gas increases in the forward direction there. So this is the effect of pressure in accordance with Le-Chatelier's principle. Now to sum up, low pressure favors those reactions which are accompanied by increase in total number of moles, and high pressure favors those reactions which takes place with decrease in total number of moles. However, pressure has no effect on an equilibrium reaction which proceeds with no change in total number of moles. So these are the three factors. Let's see the effect of change in volume. If the volume of a gaseous reaction is decreased, the pressure exerted by the molecules will increase. Thus, the effect of decrease of volume is equivalent to the effect of increase in pressure, as the effect of increase of pressure is to shift the equilibrium in the direction in which the number of moles decreases. Hence, the effect of decrease in volume will be to shift the equilibrium in the direction in which the number of moles decreases there. Now look at the question and see how to solve it. The question is, which of the following reactions will get affected by increasing the pressure? Here the question is increasing the pressure. Mention whether change will cause a reaction to go into forward or backward direction there. So here you see COCl2 gives CO plus Cl2. So 2 moles are present on the product side and 1 mole. Always see, we will consider gaseous reactants and products. So 2 moles on the product side and only 1 mole on the reactant side. So number of moles on the product side is greater in comparison to the number of moles on the reactant side. So with increase in pressure, the reaction proceeds in the backward direction there. Similarly, take the case of CH4 plus 2S2 gives CH2 plus 2H2S. So here number of moles on the product side is 3. Number of moles on the reactant side is also 3. So no effect will be there. Next you see number of moles. Carbon dioxide plus C gives 2CO. Number of moles on the product side is 2 and number of moles on the reactant side is 1. So 2 is greater than 1. So with increase in pressure, the reaction proceeds in the backward direction. Look at the next question. 2H2 plus CO gives CH3OH. 1 mole of CH3OH on the product side and 3 moles on the reactant side. So since the number of moles on the product is less in comparison to the number of moles on the reactant side, the reaction proceeds in the forward direction. Then calcium carbonate gives calcium oxide plus carbon dioxide. Number of moles on product side is 1 and reactant it is 0. So since the number of moles on the product side is greater, with increase in pressure, the reaction proceeds in the backward direction. Next, 4NH3 plus 5O2 gives 4NO plus 6H2O. Here 10 moles of products are there and 9 moles of reactants are there. Again, product number of moles on product is greater in comparison to number of moles on the reactant side. So the reaction proceeds in the backward direction. So to attempt such questions, you compare the number of moles on product side with that of the reactant. If the number of moles on the product side is less in comparison to the number of moles on the reactant side, the reaction with increase in pressure will proceed in the forward direction. But if the number of moles on the product side is greater in comparison to the number of moles on the reactant side, the reaction proceeds in the backward direction. That is the concept you need to remember. Next you see here, we'll see here, describe the effect of addition of hydrogen, addition of CH3OH, removal of CO and removal of CH3OH on the equilibrium of the reaction. And the reaction is 2H2 plus CO gives CH3OH. This is your equation. So the first part of the question, you need to describe the effect of addition of hydrogen. So it is the effect of concentration. So if I add more of hydrogen, the reaction proceeds in the forward direction. So an addition of hydrogen, the reaction goes in the forward direction. Second, addition of CH3OH. So when I add more of CH3OH. So since it is addition of product, the reaction proceeds in the backward direction. So addition of CH3OH, reaction proceeds in the backward direction. Then third is removal of CO, carbon monoxide. So when I remove this carbon monoxide, then since this is removal, addition, reaction goes in the forward direction. Removal, reaction goes in the backward direction there. So removal of CO, reaction goes in the backward direction. Removal of CH3OH, the reaction goes in the forward direction. Addition of CH3OH, reaction goes in the backward direction. And removal of CH3OH as soon as it is formed, if it is removed, the reaction proceeds in the forward direction there. So this is how you will describe the effect of Le-Chatelier's principle, and that is how you will solve the questions related to that of your Le-Chatelier's principle. Thank you, children, and have a nice day.